Welcome to the deep dive. We take complex information, sift through it, and bring the core insights straight to you.
And today, we're tackling a really interesting research paper. It's called Conditioning Matters. Training diffusion policies is faster than you think.
Yeah, this one looks at training robots, specifically how they use instructions and what they see to, well, actually do things. These are called Vision Language Action Models, or VLAs.
And the paper introduces a new method, COCOS, designed to make this whole process much more efficient. It seems they found a key bottleneck.
Exactly. And we know you, our listener, want to get up to speed on these kinds of complex topics quickly to grasp those aha moments without getting bogged down. So think of this as your shortcut.
Our mission then is to unpack why training these VLA models is surprisingly hard, what this COCOS method actually does to fix it, and maybe most importantly, why it matters for the future of robot learning.
We've got the full paper here, abstract, intro, methods, results, the whole deal. So let's dive right in. Where do they start?
Well, they start with something a bit counterintuitive. You'd think generating robot actions, a sequence of movements, would be simpler, maybe less complex, than generating, say, a detailed image or a long piece of text.
Right. Fewer dimensions involved, technically.
Exactly. But training these VLA models for robots turns out to be really difficult and takes a lot of computational power. It's surprisingly resource intensive.
So it's not just about generating the arm movements themselves.
That's what the researchers argue. They believe the real challenge isn't the action generation per se, but how well the model understands and actually uses the information it's given the visual scene and the language command. They call these the conditions.
Okay, the conditions. So the understanding part is the bottleneck.
Yeah, and they have this term for when it goes wrong, condition omission.
Condition omission.
And it's when the robot's policy, its control system, basically fails to properly integrate or act on those visual and language instructions. It might see the object, hear the command, but the resulting action doesn't really reflect that input.
So like the information goes in, but doesn't really influence the output.
Pretty much. They even ran an experiment to show this. They compared policies trained completely from scratch versus ones that used a pre-trained vision model, Dino V2, which ours has a good understanding of visual features.
Okay, so one group had a head start on vision.
Right. And while the pre-trained ones did better overall, even they showed this tendency to sometimes ignore the conditions. Their actions didn't always match what they were seeing or being told.
That's fascinating. How did they measure this ignoring behavior?
They looked inside the model, essentially. They examined how much the internal representations, the policy network's hidden states, changed when the visual or language condition was provided. And the key finding was, less change meant the model was paying less attention. If the internal state didn't shift much, it suggested the condition wasn't really being used to shape the decision.
So less internal reaction means it's kind of tuning out the instructions.
Exactly. And this leads directly to the core problem they identify in the paper. Loss collapse.
Loss collapse. Okay, that sounds bad.
It is, for the training process.
Yeah.
Basically, if the robot's network struggles to tell the difference between different conditions, like it can't clearly distinguish move left from move right based on the inputs, then the training kind of gives up on learning specific actions. Instead, it starts optimizing for just the average action, something that might be vaguely okay in either situation, but perfect in neither.
Oh, I see. Like the analogy they use, teaching someone left or right, but they just treat both instructions the same. They end up just moving a little bit in the middle, maybe?
Precisely. They fail to follow the specific command because the distinction is lost on the model. Figure 3 in the paper shows this really clearly, a policy getting move left or move right instructions, but just performing this kind of average non-committal action.
So the model essentially gets confused and just defaults to a mediocre middle ground.
You got it. And that's loss collapse. It prevents the model from learning fine-grained, condition-specific behaviors.
Okay, so problem identified. Condition omission leads to loss collapse. Robots learn average actions. A bit of a mess. So what's the proposed solution?
The solution is called COCOS. That stands for Conditioned Source Distribution.
COCOS?
Yeah.
All right. How does it tackle this loss collapse?
The core idea is actually quite elegant. Normally, these diffusion models start generating an action sequence from a standard, generic starting point, technically, a standard Gaussian distribution. Think of it as a random zero information starting point.
Okay, a blank slate each time.
Right. What COCOS does is it changes that starting point. Instead of being generic, the starting point is specifically tailored based on the visual and language conditions the robot is currently receiving.
Ah, so it gets a hint right from the beginning, based on the situation.
Exactly. It's like giving it a more informed initial guess.
Figure 2 in the paper illustrates this. The standard starting point is replaced by one that depends on the condition C.
And how does it create this condition-dependent start? It uses a component called an autoencoder. This part of the network learns to take the visual and language information, compress it down to its essence, and then use that compressed representation to set the mean of the starting distribution.
Okay, so it encodes the condition to adjust the starting point center. What about the uncertainty?
Interestingly, they keep the uncertainty, the standard deviation, fixed. It's the center of the starting noise distribution that shifts based on the condition.
Got it. And the benefit is?
The benefit is huge for avoiding loss collapse. By making the starting point itself dependent on the conditions, COCOS forces the policy network to pay attention to those conditions right from step one of action generation. It has to process the condition to even know where to start.
So it prevents the training from just ignoring the inputs and collapsing to that average action we talked about.
Precisely. It bakes sensitivity to the conditions into the very beginning of the process. And they back this up theoretically, too, with Theorem 1, showing how this approach helps avoid the mathematical pitfalls leading to loss collapse.
Okay, makes sense. So practically, how do they implement this? You mentioned the autoencoder.
Right. The autoencoder's job is crucial. It needs to learn a good compressed representation of the visual and language inputs so that the adjusted starting point it provides is actually meaningful and helpful.
And how is it trained?
They describe two ways. First, a two-stage process. Train the autoencoder first on the condition data, then freeze it and train the main robot policy using the COCO starting points.
Okay.
But they also found a simpler approach works just as well. Train everything together, the autoencoder and the policy jointly. They use a technique called exponential moving average, EMA, on the autoencoder weights during this joint training to keep things stable.
Joint training sounds more practical. So the big question, did it work? What did the experiments show?
This is where it gets really convincing. They tested COCOS extensively. In simulation, they used benchmarks called Libero and MetaWorld that's 70 different tasks combined.
Wow, okay.
And importantly, they also tested it on real robots, a low-cost one, the SO100, and a higher-performance industrial arm, the XARM. Again, across a range of tasks for each pick and place, wiping, unfolding cloth, pouring, about 10 diverse tasks per robot.
That's comprehensive. So what about that first research question, training speed and final performance? Did COCOS deliver?
It really did. The results were significant. On Libero, for instance, COCOS achieved the same performance level as the baseline model, about 2.14 times faster.
More than twice as fast.
Yeah. And it didn't just train faster, it also reached higher final success rates. On average, about 8.3% higher on Libero, and a really substantial 25.7% improvement on MetaWorld. Figures 1 and 4 in the paper show these learning curves really clearly steeper climbs and higher peaks for COCOS.
Those are major gains, especially on MetaWorld. What about the second research question linking this back to condition, omission, and loss collapse?
This is another striking finding. They found that COCOS allowed smaller models to perform remarkably well. A COCOS-trained model could match or even beat much larger pre-trained VLA models like Zero and OpenVLA OFT.
Really? So smarter use of information trumped sheer model size?
It certainly looks that way. COCOS even outperformed another model called Seer on a particularly difficult task. It suggests that effectively conditioning the model is perhaps more critical than just scaling up parameters. You can see the comparisons in tables 1 and 2.
That's a powerful point. Quality of conditioning over quantity of parameters. And did they confirm COCOS actually made the robot use the information better?
Yes, they went back to those internal state measurements we discussed earlier.
The hidden state changes.
Exactly. They measured things like cosine similarity changes and norm scale changes in the policy network's hidden states in response to the conditions. And consistently, the models trained with COCOS showed significantly more sensitivity. Their internal states changed more drastically based on the input.
So, proof that COCOS wasn't just, injecting noise, but actually making the network more responsive to the visual and language cues.
Precisely. It confirms that COCOS helps tackle that core condition-omission problem.
And what about the real-world robots? Did the improvements hold up outside simulation?
They did. Across both the low-cost SO100 and the high-performance arm, Cocos consistently improved success rates on the various tasks they tested. Figures 5 and 6 show these results and some nice visual examples of the robot succeeding.
That's crucial. Real-world validation.
Absolutely. They noted that baseline models often failed in the real world due to misinterpreting instructions or visual perception errors, things that Coco seemed to mitigate significantly.
Did they offer any specific examples or case studies that really highlight why Cocos helps?
Yes, a couple little ones. In simulation, on Libero, figure 8, they showed how baseline robots often ignored a third-person camera view, relying only on the wrist camera. If the object moved out of the wrist view, they failed. But the Cocos-trained robots were much better at integrating both views, making them more robust when, say, one camera view was blocked or less informative.
Makes sense. Using all available information. What about the real world?
In the real robot tests, figure 7, they highlighted how baseline robots could over-rely on language. If told to open the lid, they might try to open it, even if the visual information clearly showed the lid was already open.
Huh. Blindly following orders?
Kind of, whereas the Cocos robots showed better contextual awareness. If the lid was already open, they'd recognize the goal state was met and remain idle, showing they were properly integrating both the language and the visual reality.
That's a much smarter, more grounded behavior. Did they test any variations of Cocos itself, like fine-tuning it?
They did some ablation studies. They played around with the uncertainty level, that standard deviation to the Cocos starting point. They found it's generally pretty robust. Performance was good across a range of values, as long as it wasn't set too low, making the start too deterministic.
Okay, so it's not super sensitive to that parameter?
Right. And they also confirmed that the joint training approach, the one using EMA, worked just as well as the two-stage approach, which is good news because it's simpler to implement.
Excellent. Okay, quite a journey through this paper. Let's try and wrap it up. What's the big picture, the main takeaway here?
I think the core message is that loss collapse, driven by robots failing to properly use visual and language conditions, is a major bottleneck in training these VLA models.
Right.
And their solution, Cocos, which cleverly conditions the starting point of action generation on those inputs, provides a relatively simple but really effective way to overcome this. It leads to faster training and significantly better performance, both in simulation and on real robots.
And it really underscores that how a model uses information, how it's conditioned, can be just as, if not more important than simply making the model bigger or feeding it more data.
Couldn't agree more. It's about smarter learning, better integration of the inputs, not just brute force scaling.
It definitely feels like a step towards more efficient and, dare I say, more intelligent robot learning. So for you listening, here's something to chew on. How might this core idea that conditioning matters so much apply elsewhere in AI?
Yeah. Could similar collapse issues be lurking in other complex AI systems?
Yeah.
Maybe in language models or reinforcement learning agents in different domains?
And could similar strategies like creating smarter condition-dependent starting points or processing pathways unlock similar gains in efficiency or capability in those areas too?
It's a great question. And as robots get better at truly understanding and acting on the world based on multiple inputs, what new possibilities might that open up? Think about complex assembly or nuanced human-robot collaboration.
Definitely food for thought. If you want to get into the nitty-gritty, the paper itself has all the technical details.
And it's a fascinating window into the current challenges and innovations in robot learning.
Well, that's our deep dive for today. Thanks for joining us.
Until next time, keep exploring.